Okay, so let us continue. So first we need to determine what is the direction of velocity. Who will tell me how you can calculate the angle between the velocity and the horizontal line? This angle theta, how we can find it? So first I need to determine theta. What should I do? The velocity is defined as tangent to the path. Okay? Since the velocity is tangent to the path, this means that if I draw the tangent line to the curve, it will have the same direction of velocity. And from mass, you know that for a tangent line, to find its slope, the slope of it is simply that tangent of theta is equal to dy by dx. Okay? Since I have y given as a function of x, so all I have to do is to derive this relation. I have 1 over 20x squared. The derivative is 2x over 20, which is x over 10. In particular, I am interested at theta at point A. So I can say that tangent theta A is xa over 10. And since xa is 10 meters, so I get 10 over 10, which is 1. Okay, so 10 over 10 is equal to 1. Therefore, I can say that theta A is 45 degrees. So the value of theta A is 45 degrees. Okay, so now I will pass for the acceleration calculation. So I need to determine the direction and magnitude of acceleration. So first, in any curvilinear motion, pay attention that your acceleration is divided into two components, one that is tangent to the path and one that is normal. Now already we have seen that AT is given. So AT at point A is given to be +2. So I just still need to find AN. For AN, it's directed along UN, and in magnitude, it's given by V squared. So I am interested at point A, so it's VA squared, and V at A is given, it's 6 meters per second, over the radius of curvature at point A. Now, since I need the radius of curvature, and I know the equation of the path, then I should apply the relation we have seen in the previous slide to get rho at A. So let us see the details of calculation. So with the first derivative was already calculated, it's x over 10. Then I compute the second derivative of the function, which is 1 over 10. And then I am ready to calculate rho at A. To find rho at A, it's 1 plus dy by dx at A to the power 3 over 2 over the second derivative at point A. Here the second derivative is constant, so at A also it will be 1 over 10. And concerning the first derivative at A, it was calculated already to be 1. So now by replacing the first and the second derivative at A in the expression of the radius of curvature, I can get rho at A. And please pay attention, here we put the absolute value because rho is always positive. So in case already this term is positive because we have square. So in case the second derivative is negative, you should take the absolute value of it. Okay? Now, once I calculated AN, now I am ready to find the total acceleration. The total acceleration is divided into tangential component and normal component. So I can write it as a vector equals to 2ut plus 1.273 un. Now, to find the magnitude, I will do the radical. So it's radical 2 square plus 1.273 square. I still need to determine direction. And in general, when I ask about direction, give an angle with a fixed reference. So in general, we give it with the horizontal or the vertical, because UT, UN are always changing. So we prefer to give the angle with a fixed direction. This is why here, if we do a small figure, we have UT vector is doing an angle of 45 with the horizontal because it's along the tangent line. So we already know that this angle between UT and the horizontal is 45. And UN is perpendicular to UT. So we have here an angle of 90 degrees. Now, how to determine what is the angle, let's say, between the acceleration and the fixed reference, which is the horizontal line? So if I want to represent the direction of my total acceleration, the technique is as follows. Since I determined AT and AN, so I know these two components, I can find the angle between UN and the total acceleration. I can find phi by simply saying that tangent of phi is AT over AN. Okay, so AT is 2, AN is 1.237. This will allow me to calculate this angle phi. And once I obtain phi, by simple geometrical calculation, I can see that the angle with the horizontal here can be calculated as phi minus this angle, this one, which is 45 degrees. Okay, why it's 45? Because you know that this is 90 and this is 45 and the whole angle is 180. So the angle between UN and the horizontal will be 45 degrees. And since the angle between UN and A is 57.5, then I can say that I can represent the acceleration vector by an angle of 12.5 degrees with the horizontal, which is equal to the difference between the big angle phi, which is 57.5, minus 45 degrees. Any question on this problem? Winnie, Marissa is here. She's not here. I can dust this up. Okay, yeah. Let us continue. The race car C travels around the horizontal circular track that has a radius of 90 meters. If the car increases its speed at a constant rate of 2.1 meter per second square, starting from rest, determine the time needed for it to reach an acceleration of 2.4 meter per second square. What is its speed at this instant? So this is another problem of curvilinear motion, but now it's a circular motion. So the radius of curvature is constant and it's equal to the radius of the circle. So here rho is 90. Now, they are telling us that the car increases its speed at a constant rate of 2.1. This means that since this represents the variation in speed, so it's AT. So from this sentence, we can write that AT, first it's plus because it's increasing, the speed is increasing, so plus 2.1. And the second important information is that AT is constant. So AT is constant. Now, they are telling us that the system is starting from rest. So V0 is equal to 0. And we want to determine the time needed for it to reach an acceleration of 2.4. This acceleration of 2.4, when I just say acceleration, this means this is the total acceleration, okay? So we know the magnitude of the total acceleration. We need to determine what is the time needed to reach this acceleration and what will be the corresponding speed at this instant. So the first thing to write is that the total acceleration is equal to, we can put directly square, and here it's the radical, or you can put that the total acceleration square is equal to an squared plus at squared. Okay? Now, already you have that the total acceleration is given. So I can replace a by its value, which is 2.4. So I get 2.4 squared. I replace at by 2.1. So I can get the value of an. Okay. Now, since I am interested in the time needed to reach this position, I should express an function of time. How to do this? We know that by definition, an is v square over rho. And here rho is given. It's 90. Okay, it's 90 meters. Since I need time, and look, they asked for time before the speed. So before getting v, I should get the time. This is why I should replace v by a function of time. To do this, I should write the relation between v and at. I know that at is dv by dt. And since it's a constant, then I can apply the rule of constant acceleration. So I can replace the velocity v simply by 2.1t plus v0, since at is constant. And because it's starting from rest, so v0 is 0, then I can simply write that the velocity v is the constant tangential acceleration 2.1 times t. So if you replace v in its function of time in an, then you will get in this equation one variable, which is time. So if you replace an by its function of time, you can get the time t to reach the total acceleration of 2.4. And once you find t, you just replace into v equals 2.1t to get the speed. So let us see together the details. So as we said, first, we write that a is radical at squared plus an squared. Now, since at is constant, we can write v equal v0 plus ac times t. And since v0 is 0, since we are starting from rest, then v is just 2.1t. Therefore, an can be calculated as a function of time. And now, if I replace an by its value in the equation of total acceleration, I can get the time needed to reach at equal 2.4. And then I replace the time in velocity expression 2.1t to get the value of the speed. Any question on this problem? So we continue next time. Thank you. Bye.